So hello, everyone. We are now in week number 15. This is the last week of the course. Yes, Carla, me too. It's so sad. It's so sad. But and we gotta pull through, guys. We gotta be strong. Just be strong. Anyways, this is week 15. We are in our massive 3-day review of the material, because as you all know, hopefully, because you were here last time, the final is on campus. The final is live. The final is on Thursday, December 16th at 3 p.m. I asked people, I know it's awful. I know having to see me is just horrendous. I know. But I asked people to, what if you are sick? Do you mean like mentally sick or like physically sick? And if you mean mentally sick, physically sick, do you mean like COVID sick? Or do you mean like just run of the mill, like flu or something like that? I'm sure if you are seriously ill and cannot make it, then you can make it to one of the makeup days. The makeup days will be the following week, Monday or Tuesday. You cannot take it early. You can take it later, Monday or Tuesday. I asked people, and I did get a couple emails. I know I didn't respond to them because I've been very busy, but I did get a couple emails from people asking to meet me over the weekend or sometime after the actual final time to do it, and I'm okay with that. Finding time is the key. As long as we can do that, it's not a problem. The more people who take it on Thursday, just get it out of the way. But if you want to take it, if you feel like you have to take it later, and it's not just because I want to, or because just made up reason. Ideally, you have a justifiable reason why, for whatever reason, you can't come to school on Wednesday. One person said something about working, some big project or meeting or seminar or something that she has to do. I forget exactly the details, and that's fine. Just I'll trust you. I'll accept your valid reasons, and we will find a time for you to do a makeup. The only thing I can't do is allow you to take it early. So anyone who wants to take it has to be later. Again, I asked you this before, send me an email if you feel the need to take it later, if you don't want to come in on Wednesday, or if you're sick. Some people actually, in my last test, yes, all tests must be done in person. There is no online test for finals in the math department. So if you don't take it Wednesday, you will need to take it at the makeup day in front of someone. That much is a guarantee. I remember last time I taught a year ago, maybe 2 years ago, whatever, when COVID was still in its heyday. The math department did a similar thing where it forced people to take it in person. And one person sends me this email like, oh, I can't do it. I'm sorry. I'm so worried about COVID and this and that and whatever. And he kept going back and forth saying he really can't do it. He really can't do it. He's really scared. At the end, he came in anyway. And I said, what's the big deal? You made a whole big deal about COVID. He goes, yeah, I was trying to get out of it. But once I realized I couldn't, I just decided to come in. So he was trying to pull a fast one on me. It didn't work. If you legitimately feel that you can't come in, or you have a good reason, or on the day of the school screening process, because you have to get screened, there's an online form to fill out that says do not come to school today, then we'll get you a makeup. That being said, we're 10 minutes in, let's get started. So chapter 10, displaying quantitative data. So we know there's a difference between quantitative and qualitative data. Quantitative data gets dot plots, as we see here. Know how to make a dot plot, know how to read a dot plot. Even with X's, we still call them dot plots. You don't have to make dots, but they're called dot plots. We don't call them X plots. That's just weird. Then we have histograms. difference between a dot plot and a histogram. The dot plot, you have the actual data. The histogram, you only have ranges of data. So you might lose some information in that sense. Histograms can either count the actual number or they can count the relative frequency, proportion. They're going to look the same, assuming they're the same widths in terms of heights, but you're measuring technically something different. You should know how to do both of those. We had distribution shapes. Skewed to the right means the tail's on the right side. Skewed to the left, the tail's on the left side. Symmetric means there's, it's a mirror image across. Even this one here is symmetric. It's just not normal. Normal, we know from later, has a peak in the middle and it tapers off on both sides. It's symmetric, but it's not normal. More of this, more of this. Then we did stem plots. Another way of displaying visual data, essentially a stem plot, like a dot plot on its side. And we did a split leaf stem plot, or a split stem, where you have so much data that you divide your stems into two, like 0, 0, 1, 1, and so on. Notice here, of course, there's no data here, but we don't skip it. You still write the stem, you just don't have any data there. And that seems to be it for chapter 10. So are there any questions on chapter 10? Before we move on to chapter 11.
Nope.
Okay, measures of position. This one. So chapter 11 on measures of position. Where is the center located? We have the median. The median is something you should know. It's essentially, if you line up the data from lowest to biggest, smallest to largest, the median is essentially the middle one. We also have the 25th and 75th percentiles, which, if you recall, hopefully is the middle of the left and the middle of the right. We did percentiles in general, not just the 25th, the 50th, and the 75th, but any amount. And what a percentile means, the 65th percentile, for example, means that you are larger, or your value is larger than 65% of the corresponding population. We did cumulative percentile or percentage plots, starting at 0%, going all the way to 100%. This allowed us to help us see where the median was, 50%, and the 75th quartile or percentile, and so on. We did all of that stuff. This is the three big ones: the median, 50th percentile, and the quartiles, the 25th and the 75th, labeled Q1, Q2, and Q3 respectively. We spent some time on this. And of course, the 5-number summary puts it all together. The lowest, Q1, median, Q3, and the maximum. And we created box plots to help us visualize the 5-number summary. 1, 2, 3, 4, 5, those 5 numbers. And we compared multiple box plots at the same time. And that was it. We did all we did for chapter 11. So are there any questions on chapter 11? Or at least what you need to know. Again, I'm not teaching it right now. I taught it before. I'm just merely listing the things that you should, if you're going to focus on some things, the things that I point out as being like, these are important for this chapter type thing. So are there any questions on chapter 11?
No.
Okay.
Professor?
Yes.
I found the problem that I was asking about from last class. It was on a quiz.
Okay.
But the paper doesn't say which quiz it is. So I don't know if maybe I tell you if it may ring a bell.
Well, if you read the question, I could do it here. So go ahead. Hold on. I'm going to share my, give me 1 second. Okay, go ahead and read the question.
It says, statewide, the pass rate on the CSET exam for future elementary school teachers is 91%.
91%, okay.
And then the first part, which is really what I have a question with, is describe how to use random digits to conduct one run of a simulation that models the situation of randomly selecting 20 future teachers taking the CSET and counting the number who pass.
Okay. So we have 20 people with a 91% pass rate. And we want to model a situation for how many of 20 are going to would pass, correct? That's the question, right? Did I read it correctly?
Yes.
Okay, so what we need is a scenario where we can easily divide the possibilities into two collections, those that give us a 91% chance of success and those that give us a 9% chance of failure. And I think the easiest way is to assign the numbers from 0 to 90. These will be pass, and 91 to 99, these will be fail. Because if you look at the collection 0 to 99, there's exactly 100 of them. And 91 of them, so 91% of those numbers would fall in 0 to 90. And the 91 to 99, that's 9% of them would fall in the fails. Does that make sense?
Yes.
Okay. So now all we do is we go to a random number generator and we have all these numbers and we look at them two at a time. And we do that 20 times. So if I get 78, 26, 0, 95, 47, 32, and so on, I would say pass, 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 fail, pass, pass, and you get 20 numbers that way.
Thank you.
Does that make sense?
Yes. Thank you.
Any other questions on either this or something that we've done before or anything? Going once, twice, 3 times. How do I stop broadcasting? Okay. All right. And Harmony, yes, I just saw your thing a little earlier with the math finals in person last year as well. The math department, the chair of the math department is very, very adamant on math finals being in person. The only time it wasn't, I don't know if any of you were in CSUN a couple of years ago when there was that bomb scare. His name is Rabia Jaluli. Rabia Jaluli. And he is a very strong-willed individual. So if you think you can talk your way out of it, that's not happening. But a few years ago, there was a bomb, like someone didn't want to take a test, so he just called in a bomb scare or something. Do you guys, was anyone here on that campus a couple years ago when that happened? Or maybe, yeah, something like that. I don't remember the exact details. But you know what they did? It wasn't I think what he said is, like a week before the finals, he said, like an anonymous tip. Well, we all know what scares. No, I think it scares him. It doesn't scare him. You know what he did? He set up finals in libraries and in different buildings in Northridge. And students were responsible for traveling to all other places and taking their finals there. So even then, he had finals in person. So yeah, so that was like, I don't know, 2 years ago, 3 years ago. I know it was certainly before COVID. Maybe it was a semester before, the year before. I don't remember exactly. Anyways, so even then it was online. I mean, it was in person. All right, so let's share again. What chapter did we just do? That was
Professor, another quick question.
Yeah, go ahead.
On that same one for the exam number 1, number 8, how do we calculate the fair price?
For a fair price, you calculate the expected value. And the expected value of what you're spending and the expected value of what you're receiving must be the same so that they balance out. So if I have a lottery, for example, and I'm here, let me share my screen again. Oh, So if you, you have a lottery and you buy prize number 1. And that's, let's say, it's $100 gift certificate. And prize number 2 is, let's say, a $50 gift certificate. And prize number 3 is a $10 gift certificate. And you sell 100 tickets. You sell 100 tickets. So the question is, what is the fair price? How much should a ticket cost for this game? How much should I charge? You know, obviously, I'm not going to charge $1,000 for a ticket. Why would anyone pay that much money to get at most $100 back? And if they're free, I mean, that doesn't make any sense. I make no money. So I am going to have to pay out $160, correct?
Yeah.
Okay, so if I need to pay out $160 and I'm selling 100 tickets, you actually really don't need probability for this one. So my contrived example is the greatest. But if I'm going to sell 100 tickets and actually let's make it even easier, 160 tickets. So I'm going to sell 160 tickets here, and I'm going to have to dish out $160 at the end. So what will be a fair price to charge for a ticket so that I break even at the end? $1, right? In Katarina, no problem. It's canvas is down for the day. So 160 tickets, $160. A fair price would be $1 per ticket, so that the amount that I make is equal to the amount that I give away. That would be a fair price to pay to charge. That was not the greatest example. So let me try a different one. Let's say we play a game where I'm going to flip a coin, and if it's heads, I will give you $5. And if it's tails, you will give, well, okay, let me try this again. Yeah. Flip a coin. So you pay an entrance fee, right? You want to play the game. You're going to pay an entrance fee. If it's heads, then you get $5. And if it's tails, then you lose your fee. Okay. And the question is, what would be a good price to charge for this game to make the game fair? So I compute the expected value of my winnings. The expected value of my winnings is equal to $5 minus the entrance fee, we'll call F, minus the entrance fee. And there's a 50% chance of that, plus losing your money, and there's a 50% chance of that. So in other words, best case scenario, you have $5 minus your entrance fee. Worst case scenario, you just lose your entrance fee. And I want this to be equal to 0, so that your fee perfectly balances the cost of playing. So what do I get? I get 5 minus 2F over 2 is equal to 0. And therefore the entrance fee should be $2.50, which really, if you think about it, makes a lot of sense. Because if half the time you get $5 and half the time you lose what you give, then an entrance fee of $2.50, every 2 games, you win 1, you lose 1, you pay the fee twice to play, you win $5 back once, you break even. Does that make sense?
Yeah. So why did you add the 1/2?
Because it's the amount times the probability of it occurring. There's a 50% chance of heads and a 50% chance of tails.
Yeah. Okay.
So it's the amount times the probability plus the other amount times its probability. You add them together. That's the expected value. We want that to be 0, so we can solve for the fee. We can solve for F.
Right, so then like how on the exam it was a wheel, you would divide the total number of money you could win
Okay,
by the possibilities, right? By how many options?
yeah. Well, by the probability of it occurring, not how many options, but how likely it is for that to occur. So if there's 8 sections of the wheel and 3 of them would have you win that, then that would be 3/8. That's the likelihood of that occurring. Does that make sense?
Yeah, it does, thank you.
Okay. Can I ask a question from chapter 6? Yeah, I don't see why not. Go ahead.
It was the area model one. I think I'm just making those a lot more complicated than they actually are.
Okay,
Should I give you the one that we did?
sure.
It was 3 out of 5 people sing in the shower.
3,
Oh, wait, no.
5, 6. Okay,
I'm sorry, wait, it wasn't that one. It was the other one, but I didn't write it down. I don't know if maybe someone else would have it.
I don't know what it is.
It was one with like people aged 18 to 34 and 55 and up, if anyone else knows what that one was.
Yeah, I have it. It says 70% of 18 to 34-year-olds shower for longer than 10 minutes, while only 30% of people aged 55 and older shower that long. Suppose you pick an 18 to 34-year-old at random and a 55-year-old at random. You want to find the probability that both shower for longer than 10 minutes.
Okay, so what we're gonna do is we're gonna make an area model. And we're gonna divide up the vertical into 10 equal parts. And the horizontal into 10 equal parts. And I know they're not all equal parts because I am not amazing at drawing, but try to go with me here. And these will be the young and these will be the older people. So for the young, 70%, 1, 2, 3, 4, 5, 6, 7. So five, 6, 7. So 70% of the young is that area. Would you agree with that?
Yes.
And of the old, we want 30%. So that's 30% of the old. And the overlap is that, which you can see is 21 of 100 or 21% of the squares. So if we pick somebody at random with a 70% chance of the first event occurring and a 30% chance of the second event occurring, then there's a 21% chance that both occur. That's the area model approach.
Thank you.
No problem. Does that make sense, everyone?
Yes.
Any other questions you want me to go over? Just give me 1 second, everyone. Hold on, please. But yeah, sorry. Okay, so let me go back now to unless there's any other questions to our review. So we just did number 11 or 12. We did 11. So now the 12, the mean. Okay, what do we have to know here? You have to know the mean. Right, that's one of the big ones, the average. You add up all your data points, divide by how many you have. You should, yeah, you have to know that one. And we had a few different models of how to find the mean. I remember we had a quiz on this. There was the balance points idea. There was the leveling out idea, and there was the equal redistribution of wealth idea. All three of them you should know how to do. Of course, plus the formula to actually find it. We talked about the differences between the mean and the median, and when you would use the mean and when you would use the median. We certainly spoke about that. And let's see what else we have here. We talked about weighted means a little bit. I wouldn't worry about that though. Yeah, I mean, out of all, we have an entire chapter of stuff to ask on. So I'm not gonna ask on something that is covered on one page at the end of one chapter. So I wouldn't worry about the weighted mean at all. But just for completeness, how do you do the weighted mean? Well, you want to average two or more things, but they're not equally weighted. You don't just add them up and divide by how many you have, but you can multiply each by, it's basically an expected value. You multiply each by its corresponding probability, add them all together, and the expected value formula gives you the value of the weighted mean. So yeah, that's it. Okay, so that takes care of chapter 12. Are there any questions for chapter 12? Oh, okay. Now let's keep going then to, oh, I had the wrong question. Wrong button. So let's go now to 13. 13 is variability. Variability. So we have measures of position, center, mean, median, and mode. I don't know if I spoke about the mode so far today. Did we cover the mode in class though, right? The mode being the one that occurs the most often. That's not, I'm not being delusional here, right? We covered that? Yes, I believe so. Mode, I think so, yeah. It's just the one that occurs the most often. But now we're dealing with variability, the spread of the data, how widespread it is. Is it really clustered around its true value? Or is it really spread out and you have small and big and all over the place? The more the spread, we want to measure that. And we had three ideas, three ways of measuring spread. We had the IQR, the interquartile range, the mean absolute deviation, the MAD, and then we had the standard deviation, the STDEV. And of those three, which one is not used in practice? Who remembers? Which of those three is not used in practice?
Mean absolute deviation.
Yes, excellent. The MAD, the mean absolute deviation, is just a mathematical contrivance to help us understand the standard deviation, which is more mathematically involved. Yeah, when it comes to actually doing calculations, the mean absolute deviation is a lot easier to work with, so you should certainly know it. We talked about the range and why we shouldn't use the range as a measure of spread. The IQR is the length of the box of our box plot. It's Q3 minus Q1. We talked about that and how to use the IQR if we're going to use the median as our measure of center. And then of course we did the MAD and talked about that and kind of developed it from scratch and got to this formula here. And I don't know if I mentioned this, but you guys want a cheat sheet on the final? What do you guys want? You guys want to do it by heart or a cheat sheet?
Cheat sheet.
I think we should take a vote. Who here wants a cheat sheet? 1, 2, 3, 4. This is gonna be a close, I think. I think we got to use our notes. Okay, fine, even better, use your notes. So forget cheat sheet, use your notes, bring all your notes, bring everything. Don't bring your videos because you can't listen to them. No, let's use a cheat sheet. Instead of notes, you prefer cheat sheet over notes? Okay, fine.
No, notes.
No notes? My tutor, you have a tutor for this class?
No, like, I mean, yes, let's use our notes.
Oh, because you said no notes, and I'm like, oh, okay, no notes, that's kind of weird. So, okay, so you want notes then? Okay, fine, notes it is. Bring all your notes, however.
What about both?
Okay, you can bring both. Notes and a cheat sheet, I will allow both. That's fine. However, can we bring the homework answers? Sure, bring the homework. Oh, that's a lot, that's asking a lot. Can we bring the what the hell, bring the homework answers. So, yeah, why not? Just one thing though. Don't just rely on these notes and the homework solutions in your cheat sheet. If you're looking back and forth nonstop during the test, you probably will not have enough time to finish. So your notes, this goes for every class. Your notes are there for formulas that you don't want to memorize or just in case. But when you rely upon your notes, it's usually not a good thing. And the final is, yes. Oh, you think I forgot? Yes, the final is 20%. I didn't forget that. I forget many things, so it's probably not the worst idea to remind me about that. But yes, I think it was 15% for that first test and 20% for the final. So mean absolute deviation, we talked about that. Then we got to the standard deviation. We spoke about that as well, of course. This is the big one. This is what we use when you're dealing with the mean. IQR goes with median, this goes with the mean. Why do we divide by n-1? That was a technical thing. No,
Professor, will any of our the quizzes be getting dropped anymore? Like our lowest quiz grade?
well, we didn't have how many quizzes do we have? Like 6, right?
Yeah.
So I was supposed to give you 8 and then drop 2. I only gave you 6.
Okay. Sounds good.
So I think a good trade-off would be just to keep the 6 grades and then take 20% from the final for that first test. I think that's a pretty good trade-off. Is that
Okay.
fair?
Yeah.
Yeah, I
Yeah,
think so.
sounds good. Okay, thank you.
Okay, and then comparing the measure of the variability. IQR is used when it's strongly skewed, which is when we use the median. The MAD is used mainly to introduce the idea, and the standard deviation is used mostly for the mean. So those are the ideas for chapter 12 that I want you to know or to focus on. Are there any questions on variability? Okay, that takes us to the end of 13. And then we did the normal model, 14. Yeah, this is the big one. This is important, okay? You'll definitely be getting at least one question on the normal model. The normal model is used for most natural events of this kind have a value. The typical value tapers off to either side. The length of a centipede or any kind of animal is normally distributed. We had the 68, 95, 99.7 rule, which says that if you go one deviation either direction, that's 68% of your data. 95%, that's 2. 99.7%, that's 3. And when you hear the term almost all values, that means 3 deviations from the mean, 99.7%. And a typical value would be within 2 deviations of the mean, 95%. And then we did Z-scores. These are ways to compare 2 different distributions that might have different means and different deviations. We had a quiz question on that. This was I believe it was the Lisa and Maggie Simpson question. How do you compare different Z-scores? Of course, the paragons of virtue here. And then we had percentiles and z-scores. And how to get from the z-score to the likelihood of being beneath it, the probability beneath it from a table. Or from the calculator if you know how to use it. And how to go back and forth. And we had t-scores. T-scores are related to z-scores via this formula and just a slightly different way of comparing two different data sets. Although I've got to be honest, I've never in my life seen t-scores outside of this class. But if you have your notes and homeworks, then it's certainly within the realm of possibility that I'll ask on it. And that is what you need to know for the normal distribution. Any questions so far? Moving right along then. Chapter 15 on scatter plots. So we talked about scatter plots. You have quantitative data in 2 dimensions, possibly categorical, that adds a flavor to your scatter plot with different colors or shapes or something like that. But essentially what we're looking for is whether or not there is a overall linear relationship between the data points. Linear does not mean on a line like it does in algebra, but rather if it's clustered around a line, the more clustered it is, the more linear it is. And each dot here is a data point. And we see that the curve is non-linear. But if I didn't have that curve and I had no idea what these dots were, I'd probably draw something similar and it would be linear. So sometimes in context, you have to know what's going on to be able to determine whether or not there's a linear relationship. Strength of a linear relationship, I mean, if it's perfectly linear, if it's very strongly linear, or less strong, moderate, real moderate, kind of weak. And essentially here, I can't even really assign it a direction. And when you can't assign it a direction, it's not linear at all. That has a correlation of 0. Positive correlation indicates that it's going up. Negative correlation indicates that it's going down. That one certainly has a correlation of somewhere near 0. And correlation goes between what 2 numbers? What 2 numbers is correlation always between?
1 and -1.
1 and -1. All correlations are between 1 and -1. Not 0 and 1, but 1 and -1, because it could be negative. Positive on the way up, negative on the way down. And of course, if it's 1, it's perfectly linear on the way up. If it's -1, it's perfectly linear on the way down. And the closer it is to 1 or -1, then of course, the more linear it is. Outliers. We spoke about outliers, how you can have an outlier in 3 different categories. It could be an X outlier, like this one here, C, is an X outlier. It's out of the trend of X values, but it's within the trend of Y values, so it's only an X outlier. B is a Y outlier. It's not out of the realm of normal points in the X direction, but it is in terms of the Y direction. E is an outlier for both X and Y. And then A and D are not X outliers for X and not outliers for Y, but it's only when you look at X and Y together that we say that they are outliers. So we have outlier for one variable, but not the other, for both, and only an outlier jointly when you consider them both. So we definitely spoke about that. We spoke about independent and dependent variables. What's the difference between an independent and a dependent variable? Or 2 variables that are either independent or dependent. Essentially, variables are independent if the existence of one has no effect on the other. For example, whether it rains today in California or anywhere in California versus whether my coin that I flip is heads or tails. I mean, why does one have anything to do with the other? And spoiler alert, it doesn't, which is why they'd be independent. And if they're not independent, then the answer is that they are dependent. The big one, association does not prove causation. Okay, just because two variables are associated does not automatically mean that one causes the other. In fact, here's just in the pictures, there's a very famous association between foot size and reading level. And apparently the bigger the foot, the higher the reading level. But of course, that's because the bigger the foot, the older the kid, the higher the reading level. There's a lurking variable behind the scenes that explains why one's associated with the other. It doesn't cause the other, it's just there is a connection between them. So know that association does not imply causation. Doesn't mean it doesn't have causation, it just doesn't imply causation. Any questions on chapter 15? And then we move on to chapter 16, which regression. So regression is using a line to make a prediction. Where does the line come from? It's called the line of best fit. It's the line that best fits the data. Here's the data, and this line, more than any other line, best fits the data. And the notes talk a little bit about how to construct it. And it goes through some dead ends, and no, this is wrong, this can't be right, this can't be right, this is in the right direction. But at the end of the day, you just got to know it. So where does the line of best fit comes from? Well, it comes from the fact that if you draw a line, you can compute the residuals, which are the vertical distances between the points and the lines. And if you square those residuals and add them all together, out of all the lines that you can possibly draw, the best fit line minimizes it. It is the least squares best fit line. For that reason, it's the one that gives the lowest value of the sum of the squares. And where does it come from? It's here somewhere. I thought it gave it to us. So this chapter does not actually compute it from scratch. It just gives it to you, and you have to know how to use it. So y equals mx plus b. It's a line after all. And the best fit line, the least squares line, is a line of prediction. It's not just a line that best fits the data. Great, you drew a line, fantastic. What's the point of that? The point is that I can use the line to predict the most likely outcome depending on the scenario. If I say, okay, I have a new situation, whatever the context is, of a value of 50, what y value do I think 50 is going to be? I go up to the line at 50 and say, it's over here. Whatever the y value is, whatever the line tells me I would get. I know I might get anything. Well, dots are all over the place. But if I had to give one value and say, this is the most likely outcome, it's the one that the line would tell me. That's what the line does. And again, nowhere in this chapter do we actually find the line. Does that make sense? Hopefully. Again, this is a review. I'm not teaching this. I'm just going over what we've done before and what you need to know. So that was 16. I skipped 17. I skipped 18. And 20 starts on the third section of the course on testing statistical significance, the last few chapters, the last few. So we will do that next time. I will now entertain any questions you have on anything that we either covered last time or today, or questions about the final, or any other questions you have. But in terms of actual instruction, that's it for today. So do you have any questions for me?
So you said that chapter 17 and 18 aren't going to be on it?
Uh, 17 and 18. Yeah, we didn't do 17 and 18.
Okay.
I don't, wait. Hold on. I think we did 17 actually. 1 second. Yes, 1 second. We're not quite done yet. We did do 17 as well. So let me go and here's 17. Okay, 17. More on correlation and regression. So correlation again was that R value was how much of an association there is between the two variables. Regression is for the best fit line. We did a little bit about coming up with this formula, which you never really use it. Your calculator does it for you, but in theory, this is the formula to calculate R, to calculate the correlation coefficient, where you have your average of your X's and your standard deviation of the X's, your average of the Y's and the standard deviation of the Y's, and so on. A lot of derivation for having an idea why a positive value of R would indicate a line that goes up and a negative value of R would indicate a line that goes down. What we did talk about was your R squared value and its physical meaning. We know that the Y values, if you look at this chart, the Y values are not all the same. Why are the Y values not all the same? Well, part of it is because the X values aren't all the same. And part of it is because even if the X values were the same, there's always other things that we're not considering. The R squared value is the percentage of the variability that can be explained away by your correlation, by your association, by your regression line. The rest of it, other factors, is the other percentages. So if I have an R squared value of, let's say, 0.64, that means 64% of the variability in the Y values can be explained by the study, by the regression, and the other 36% other things that I'm not considering. A very qualitative, important understanding. We did some math here to calculate R squared. I'm not going to ask on that, so I wouldn't worry about that. But you should know this. You should recognize the relationship between this and your R squared. The sum of squared residuals divided by the total sum of squares and how it connects to R squared. You should certainly know that. The formula for the best fit line right here. Know the formula for the best fit line. I might give you some data like in this box here and ask you to use that data to compute the line and therefore to make predictions. You should know how to do that. The regression effect, if you recall, we spoke about the regression effect as data tends to approach the average, to approach the mean. So if you're taller than average and you have a child, they'll probably more likely be shorter than you and therefore get closer to the average. And if you're shorter than the mean, they're more likely to be taller than you, again, to get closer to the average. We're always trying to regress towards the mean, which is why it's called the regression effect or the regression line. And then we just summarized it, so there's nothing new there. And that is then the end of 17. And we did not do 18. I remember skipping 18. And did I ever put I can't even put the homework up right now. And yeah, I can't get on Canvas, or can I? No Canvas yet, so I'll make sure all the homework's up on Canvas as soon as I can, but right now I don't have that option. And now we're done for the day. So again, any questions on anything we went over so far?
Did we do chapter 8 or no?
8? No, we definitely skipped 8.
Okay.
No, yeah, we certainly skipped 8. That I remember for sure.
I have a general question.
General Grant or General Lee?
Huh?
Never mind, go ahead.
So do you know if we're gonna need a calculator?
God damn it,
yet?
guys, that was funny. Sorry, go ahead, what?
Do you know if we're gonna need a calculator yet?
You should certainly bring a simple calculator just in case. I don't imagine you'll need one with some of the more advanced stuff. but you should certainly bring even a basic calculator to use.
Okay, so just a basic one, right?
Yeah, just in case, just
So
in
I don't have to go out and buy like a really expensive one.
Yeah, not for one test. But
Okay.
you should certainly bring a basic one, which some people, I mean, they're all over the place. People can, some places give them out for free. They're that basic. Just, you can't use your phone, but bring a basic calculator just in case.
Okay, sounds good. Thanks.
Okay? Anyone else have a question? General or otherwise?
Yeah, so I don't know if you talked about this or not, but on the syllabus, it says you're gonna drop 2 of the test scores. Are you still doing that?
I did speak about that. So again, no, I only gave 6 quizzes instead of 8. And as a trade-off, I'm
Yeah.
taking 15% of your final grade and putting on that first exam. So I thought that was a fair trade-off to make in this regard. So the quiz scores are gonna stand. If you have a worry about that, then just send me an email. Okay, and I'm always gonna try to work with everyone to make it fair and make everyone happy as much as possible. So if there's a concern, just send me an email, okay? And yeah, the final exam is worth 20%. And I see, just checking, that math 211, now it's at 89%. 31 of 35 people have done the survey. So again, if you have not, if you are one of those last 4 holdouts, there it is in chat. Please go ahead now and fill out that survey, the last 4 of you. If I can get 35 of 35 response, that would be amazing.
Attention students, please, if you have not turned in a
Hold on.
COVID test.
All right, sorry about that.
If you still need to do the COVID test, please come pick one up in the office. Thank you.
You're welcome. So, yeah, anyway, yeah, that's about it for today then. I'm gonna stop recording.